what is this actually good for? That's a great question. And one thing it's good for that is already out there, you could buy today, is the Toyota Mirai. The Toyota Mirai is a fuel cell car. It is one that is not selling at all, right now. That's not because it's not that the technology is not proven or that's not a good idea. It has some other competing problems it's competing against. One is very cheap gasoline, right? But this car, it doesn't have a drop of gasoline inside of it. It does have a battery pack. It doesn't need one though. Just like this little car has no battery pack inside of it, it's generating electricity in real time that turns its engine. These could operate in the same way. In actuality, they do have a small battery pack, but there's no, this is the only thing that you have to have this is some way to perform electrolysis to start with, right? In reality, they don't have you splitting water in this car. They expect to sell this car where you're going to have a place that has hydrogen tanks that you could fill up. Right now in Salt Lake City, I don't know if there's anywhere you could go and say, fill up my hydrogen tank on my car. So I don't know if you could buy these here. I could be wrong on that. Some cities, I know LA has these things. In the future, maybe that will be how cars move around, right? Cities will, instead of having gasoline stations where you fill up gasoline, it'll have a pressurized gas where you can fill up instantly, which is nice, more or less. And you put hydrogen in your tank. So the problem is this. Well, what's the problem? What do you guys think? Carl's saying Hindenburg. He's making some explosion hand motions. That's the problem. The reason why these things are not more popular and used right now, there's a couple things. First off, it's a hydrogen fuel cell, and this one, wherever it is, up there, that works off of a different principle that I just showed you. The one that I showed you looked like this, where we had oxygen ions moving across the membrane. This can only really happen very fast at high temperatures, like 700 Celsius. So just starting to glow, right? So that's pretty hot. Anytime you have something hot, now you have to deal with thermal expansion, you have to deal with heat management. It's not an unsolvable problem, it's just a problem, right? So that little car works off of not YSE. It actually uses a material called Nafion, which is a polymer, and it's a polymer that actually allows H plus ions to move this way rather than O2 minus going the other way, right? So it's a proton conductor rather than an oxygen ion one. These also exist for, like the Mirai doesn't use Nafion, it uses YSE. So the problems are, you have hydrogen, you have to store the hydrogen, you have to make sure the hydrogen doesn't explode. This thing's really hot. You just have a lot of things to deal with. Will it be the future? I don't know. I think that electric vehicles are probably outpacing it. I think that Tesla is going to make us a better vehicle than this, but I could be wrong. But it exists today. It's a technology that absolutely works. It's better in non-automotive settings. If you want to just have a way to have power generating, it's much better. For imagine that you're trying to generate power. How about you're on the moon, right? Let's say we follow Elon Musk to Mars or to the moon or wherever he's going, right? If you have water there, that now acts as a battery because you can convert that water to hydrogen and oxygen and then recombine it. So it acts as a battery basically, but you have to have a fuel cell like this. Okay, so if you're just coming in, tests are up here, the beginning of the alphabet, middle, and the end of the alphabet. So come grab your exam when you want to, or I'll just take them back to my office and you can get them anytime. This is what the exam looked like. We had a few people, even before the curve, almost aced this exam. We got a 95 was the high this time, which is terrific. That said, the average was lower than 80, so I curved it up. So the grade that you see on the inside booklet of your exam is 21 points lower than the one that is recorded online on Canvas. If you are the one individual in this class who does not have a Canvas score, you're the person who didn't write your name on your test, we don't know who you are. So you need to come find me if you want to be graded for this exam, okay? And then, just in case you came in late, mechanical engineers actually slightly edged out the material science students, which makes me, I don't know if I'm happy or sad about that. It just is what it is. That is exactly what it is. This is winning on the road. You're absolutely right. That's something to be proud of. Okay, today, what are we going to talk about? We are going to talk a little bit more about fuel cells and defects. We're going to talk about edge and screw dislocations. We'll talk about something known as the Burger's vector right after lunch. We have stacking faults and twinning faults. Those are our two-dimensional defects. And if we have time, we'll get into grain boundaries, domains, and maybe even talk about different microscopy techniques to actually look at these defects. So we know that they're hypothetically there. How do we confirm whether these defects are there? Maybe by the end of class today, we'll talk about that. Okay. And if you came in late, you missed out on the free education on hydrogen fuel cells. They're pretty radical, I think. Okay, to start with today, we left off last time. We said if you take an yttrium that's 3+, and you put it on a zirconium 4+ site, you have a problem. You're not positive enough. So you have to make up for that by either stuffing additional positive cations in there somewhere, unlikely. Stuffing extra atoms in is always unlikely. Or you have to take away some of the negative, which meant oxygen vacancies. So now we're going to flip it. Imagine now what would happen if you took niobium 5+. First off, is it going to be substitutional or interstitial? If you take a mixture of Nb2O5 and you take a mixture of TiO2, you grind these things together in a mortar and pestle, you heat it up until there's just one phase. So these two phases diffuse into each other and become one phase. What will happen? Is the niobium interstitial or is it substitutional? Is the question. Let me give you a chance to get your devices turned on. Okay, I'm going to go ahead and turn this on, so start logging your answers. Substitutional or interstitial? Remember, interstitial means that you're stuffing it in. Substitutional means you're taking one out and putting it in its place. Okay, so most people think substitutional, that's right, and the reason why is it's always easier to substitute than put an interstitial, almost always, right? Imagine I've got an extra student and all these seats are filled. They've got to go in there somewhere. It's going to be easier for them to just kick somebody out than just like sit in between two people. That would be uncomfortable, right? So substitutional is better. Next question then. I'll give you more time on this one, don't worry. All right. What defect then occurs when niobium 5+ substitutes a titanium 4+? What defect must occur? Do we have an oxygen interstitial, a cation vacancy, or a self-interstitial? And as a tip, the right way to think about this, you put a niobium 5+ on a 4+ site, what does that do to charge and how do you fix that? And then what's the most likely way that happens? Okay, answers in. Okay. The correct answer is cation vacancies. How do we know? Okay, listen up. All right, you had titanium, which was TiO2. If you put, since this is 4+, if you're going to put a 5+ on that site, we're going to say that this crystal, as soon as you do that, it's excessively positive, right? Excessively positive, right? So to fix that, we have one of two options. We can either add more negative, or we can take away some of our positive, right? Now, you guys voted that taking away positive is more likely. Why can't we just add more negative again? Yeah, the oxygen is huge. Oxygen 2- is a huge anion, and you're going to try and stuff another one of those in there. It's not happening. It's way more likely that it forms a cation vacancy, right? So then what would the formula be? right? So maybe turn to your neighbor real quick. Try and write down what you think the formula would be. For example, with yttria stabilized zirconia, we said zirconia 1 minus X, yttria X, oxygen 2 minus X over 2. So what will it be for this one? Now we're going to have titanium 1 minus X, right? Niobium X, we're going to have to modify this. Oxygen 2. So what is this modification here? Take a stab at that with the person you're next to. In other words, how many cation vacancies do we need? 1, 2, what? What do you think, Ryan? What do you think? But titanium comes in groups of what? You can't take out 1/4 of titanium. So for every okay, anybody want to take a stab at it? I already told them the answer, so it can't be them. Anybody? Harrison, what do you think?
So for every titanium you remove, you can add 2 niobium.
Oh, you're close. Think, when you put 1 niobium on there, you took out a titanium and put a niobium, that made your crystal excessively positive by 1.
1. And
so we
have the 2 minus charge, so if you remove the titanium, 2 extra oxygen, which is 4 extra negative charges.
Yeah, we're going to leave the oxygens alone. So all we're going to do is with that positive 1 charge, we're going to fix it by taking out some of our titanium. But titanium comes in groups of 4 plus. We can't take out 1/4 of a titanium. We can only take out 1. So it has to be for every 4 niobium substitutions.
Right, that's what I meant.
Yeah. You follow that though? Any questions on that? So then what would this be? So for every niobium gives us an excess positive 1 charge. We agree? 5 plus on a 4 plus, we're positive by 1. But a titanium doesn't come in the flavor of titanium 1 plus, 2 plus, 3 plus, 4 plus. It only comes in 4 plus, right? So if we take out a titanium, we lose 4. So we replaced 1 niobium titanium, we were plus 1. We took out 1 titanium, we're now minus 3. See the problem? So you have to substitute 4 niobiums. Now you have a total of plus 4 positive charge for every, and then now you can take out 1 titanium. So what does that formula look like then? Right, niobium is X. We're definitely going to lose 1 minus X. That's just the substitution. But we're going to have to lose more. What in addition are we going to lose? Minus, what would it be? Yeah, Shannon?
So we replace 4 titaniums with niobium.
Yep.
And then we take an extra titanium out.
That's exactly it.
Okay.
Does that make sense? Why?
Yes.
So what would that be then? What would this formula be? Yeah, Kylie. Yeah, so imagine you people are atoms, right? These are all titanium atoms. Ignore the oxygens for a minute. So titanium, 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 titanium. But we're going to take, I forgot your name. What's your name? Huh? Caroline. We're going to take Caroline out, and we're going to put somebody else in that's 5 plus, right? So now overall this crystal has a positive 1 charge too many. So if I took Jimmy out, now he had a 4 plus charge, right? So we were overly positive by 1, but by taking Jimmy out, now we're not positive enough by 3, right? We're 3 negative. So that doesn't work. So instead what we have to do is we have to take niobium, 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 right? We've got 4 charge that's too much built up, and then we take the 5th one and check them out. Sorry. Right? Does that make sense?
Yeah, so I thought you were saying, maybe I heard wrong, that we're going to replace 4...
Let's say substitute. We're going to substitute 4 niobiums on 4 titanium sites, and then...
Why do we take the extra titanium?
Because niobium has a higher positive charge than titanium. It's 5 plus instead of 4 plus. So if we just take 4 of those, now we've got a positive excess of 4 charges. So to fix that, we kick 1 titanium out. Therefore, this must be what? Any guess at it, Eric?
Well, I had a different question.
Okay.
So when you take that extra titanium out,
Yep.
you're leaving a hole there. So
That's a vacancy. It's now a titanium or a cation vacancy.
so overall, the energy is more, I guess, desirable by having that hole than it is by having the extra.
Yeah, we haven't talked about energy. This has to be energetically favorable for it to happen, right? You're giving it some entropy by adding 2 different types of cations. It likes that. That's disorder. But yeah, you're having bonds broken, so you're competing with that. In some systems, it will be favorable, in some it won't. Some systems form solid solutions, which is what this is. The niobium dissolves into it, and some it doesn't because it's not energetically favorable. But basically, this is going to have to be minus whatever x is divided by 4. Okay? So you'll see some examples of this on the homework. By the way, the homework is on polymers this week and defects next week. So the polymer homework will not be due on Wednesday. It'll be due next Wednesday. So the Wednesday before Halloween. So you have lots and lots of time. No stress about it. I'll have it posted probably sometime today. Okay, so that's defects in ceramics. The key thing to remember in ceramics is that defects come in pairs because you have to deal with charge. What about polymers? Is there such thing as a point defect in a polymer? And what might it be? What would a point defect be in a polymer? That's exactly right. A side group like PVC, polyvinyl chloride, has a side group of it's hydrogen everywhere except that every fourth hydrogen is a chlorine, right? So what if instead of a chlorine you had like a bromine? That could be thought of as a point defect in a polymer, okay? And just like point defects could be desirable or undesirable in ceramics, they could be desirable or undesirable in polymers. Maybe that defect is the one that allows the polymer to have the property that you're interested in, or maybe it ruins it, okay? All right, now let's move from 0D defects to one-dimensional, sometimes called line defects. So take a look at this. This is what's called a bubble raft. And in the 50s, this was a material scientist's jam. This is what they loved to work on. Bubble rafts were like a hit. They had some little machine, and they put a little soap in the water, and they create these bubbles. And so this is bubbles floating on the surface of what a little water raft, right? Why do they care about this? Because these stick together. They experience some sort of interaction. We now know what that is. Surface energy, right? Trying to minimize the surface energy. And it makes them behave kind of like atoms, except these are big enough they could see them in the 50s when they didn't have nice microscopes. So it allowed them as a proxy to sort of say, these are looking kind of like atoms, so what are we seeing? So what do you see when you look at this? Is it perfect? No, there's two things wrong with it. Where are they? Big hole. This would be a vacancy. That's like an atomic vacancy, right? There's just an atom that's just not there. What else is wrong? Something skiwampus right there. So what do we mean when we say skiwampus? What's happening? What's wrong with it? It's a nice hexagonal lattice, except around there something's wrong. You have five-sided thing, right? So some of the bubbles are a little bit bigger too. These should be monodisperse and mono-sized, but they're not. They're a little bit different sized. The thing to look for here, the best way to draw it is to draw it like this. Right? So I'm just drawing lines where these bubbles are centered on. See that? There's our problem. This is what's called an edge dislocation, right? If I keep on drawing lines like this, it's a perfectly good lattice everywhere else. But it has an extra half row of atoms that got stuffed in there somehow. That is known as an edge dislocation, okay? Now, one way to find it is to do what's called a dislocation circuit, I think is what it's called. So basically here, let's go around this. This is where we think the dislocation's at, right? Let's figure out how big is this dislocation that caused it. To do that, you start making a hexagonal circuit around this thing, and you see where it matches up or doesn't match up. So we go 1, 2, 3, 4. Is that right? 1, 2, sorry, that's only 3. So we did 3 in that direction. 1, 2, 3, right? 3 lattice parameters over, right? So let's go 3 in this direction. 1, 2, 3. Let's go 1, 2, 3. That's only 2. 1, 2, 3. Let's go 1, 2, 3. 1, 2, 3. 1, 2, 3. And we got a problem, right? We have to go that way. To finish this circuit, you'd have to go that way, right? That little vector here that makes the head and tail connect is what's called the Berger's vector, named after some dude named Jan or Jan Berger, right? So you can see these every time they go around these, they don't match up. You have something wrong, and that's because we had this extra half row of atoms. Okay? So the Berger's vector, you've got 2 options on it, and it creates 2 different types of defects. One of them is the one that we just saw, right? You have planes of atoms, and somebody went and stuffed in an extra half row of atoms right here on the left, right? That's akin to imagine you had a tube, and you sliced the tube cleanly, and you pushed one side in, right? Therefore, the defect is right here. Right, let me change the color. So our Berger's vector is right there. But the line of the dislocation runs vertically, right? Therefore, the Berger's vector is perpendicular to the dislocation line. That makes sense? It's not going the same direction. It's perpendicular to it. That, by definition, is an edge dislocation. It could also be parallel. Imagine this case. This is like a parking garage, and I've been bringing the stinking model for a week, and the day I need it, I forget to bring it. But I'll bring it next time. Imagine you have atoms which are bonded nicely, except that as you spiral around, it creates like a parking garage structure, right? These things are shifted up right here. Here's your Burger's vector, shifted up. So as you go around, you've now gone up one lattice parameter, right? Therefore, your Burger's vector is now pointing up, but your dislocation line also goes that way. So it's now parallel. So if it's perpendicular, it's an edge dislocation. If it's parallel, it's what's called a screw dislocation, right? Edge dislocation and screw dislocation. And then in the real world, dislocations can actually be both. It can have some character of both. So let's say you've got a lattice here. I'll bring a picture next time. But the dislocation line can start going this way, and your Burger vector is going that way. The Burger's vector can't change its direction, but your dislocation line can change until right here. Now your line's going this way, Burger vector that way. So it's perpendicular, but over here it was parallel. So dislocation lines can sort of weave through your material, and so it can go from being an edge dislocation to a screw dislocation and back. Okay? The Burger's vector has to stay the same direction the whole time. Any questions so far? This is just, we took a perfectly good lattice and we messed it up a little bit. And these are super common, right? You see this on Corn on the Cob. Just saw this weekend with my kid, right? Pointing out the Burger's vector right there, right? An extra half row of kernels, right? Because the thing got larger, so it accommodated by sticking an extra half row in there, right? So does it make sense that the dislocation in this plane is in the plane, but the line, the line of the dislocation comes out of the plane? It extends all the way through the material. If this goes to infinity, it just keeps on going. Any questions on any of this? There's usually more questions on this.
So where would the Burger's vector be in this case?
Where would the Burger's vector be? If you don't know, you can always do the circuit, right? So let's do the circuit. Let's say we go 3 atoms that way. We go 1, 2, 3 atoms that way, 3 atoms that way, 3 atoms that way. And that means our Burger's vector, to get back to where we started, is right there. Okay? Now, if you draw it the other way, you could end up with pointing the opposite way. That's fine. Kylie, question?
Yeah, what is the dislocation line? I can't quite tell which direction it's going.
So basically, think of the dislocation line as where does this dislocation keep going, right? Okay. That extra half row just extends into the board. This could go to infinity. It could go to just the end of the grain or whatever, right? In this case, they showed it went all the way to some point where this crystal ended, right? That becomes really important because in 2 chapters, we care about dislocations because dislocations are how you bend and flex and deform materials. If you don't have dislocations that can move, you don't get very good deformation. That's why some materials are very hard and stiff and brittle, and other ones are pliable, like copper, because the dislocations can move easily. So we'll come back to that. Any questions on this? Anything else?
Where do you choose to start drawing?
Start anywhere you like. Let's do another one. If you start out here on the very edge, we went 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The distance between the beginning and end is now that. Same. Fair enough? Again, we could have chosen to point it left or right. Same thing. Antonio. No, code.
On this right here, so like if you were saying that it's parallel, then it's going to be which one's screw?
That would be a screw. This is an edge because the dislocation lines in and out. The Burger vector is perpendicular to it. So if this was parallel, it would look like, do I have a picture? It would look like this. Okay, right here. Here's one. If you do the Burger's vector circuit, the Burger's vector shows up to be this thing, right? It's that step. You could go 4, 4, 4, and 4, but you have to step down. And that down is in the same direction that this defect extends through the crystal, just like a parking garage. It's the axis in the middle of your parking garage, right? So it's parallel, therefore it's a screw dislocation. Kylie?
So what are this defect you take the line at? Because basically it looks like the defect is a plane, where it like covers the entire area.
Yeah, it's a line actually. It would be a line. I mean, this thing could keep on continuing, spiraling all the way around, and the one thing that would be messed up is right along that line there. Is maybe the way to think of it.
The origin of
Yep.
this is your problem.
That is the origin, and therefore the stresses that this problem causes will be most severe along that dislocation core, is what it's called, the line on which it travels. So what do we mean the problems that it causes? We'll take a look at this, right? Are these atoms happy here? No, they're not happy because we messed them up, right? These things want to have some normal bond distance, and here, down below, these things got stretched apart. They don't like that, so they're in tension. And up here, we stuffed an extra row in, so they're under compression. So this gives rise to what are called strain fields. We have above the edge dislocation, we have compression. We have a compressive strain field, right? And here, below it, we're going to have tension. So dislocations have strain fields associated with them, and that becomes super important in 2 more chapters, okay? The garage one would have the same thing. It has problems around it. It's not as easy to visualize, though. And just like I said, the dislocation itself doesn't have to go in a straight line. It can weave through a material, but the Berger's vector does have to stay the same. Berger's vector is right here. Berger's vector is right here. It's not changing. It's just that the dislocation line right here comes out, so it's perpendicular, and there it's parallel. So it's a screw dislocation there that turns into an edge dislocation. Berger's vector, what should it be equal to? Just an interatomic distance, right? If this is a metal, our easiest scenario, it's just the distance between, on average, these 2 metal ions, right? Okay, we just talked about strain. So how does it affect atoms? How would this affect atoms, right? You've got strain in your lattice now from this dislocation. I guess the question is, so what? So turn to your neighbor and say, so what? Why do we care about this? Yeah, Matt. It doesn't have to be. It does not have to be a light. It could just be a talking separation. So think of FCC copper. What's the separation? It's not a whole lot. It's around like that big center. So think of things of atomic separation. Absolutely. You won't get into it in this class. In other courses, you will talk about it. Right now, it's a all the time. We'll come to that. That's a good question.
That's a good question. So, for the core of your for example, let's say there's that first added
Right now, it's a single layer. You have corners like
multiple layers. Yeah, but what if it keeps getting wider? Your core deformation kind of goes.
It's curved. That causes a flattening. Okay, so what are people thinking? What's our so what? Why do we care about these things? Obviously we do. Why do we care about there being a strain field associated with dislocations? Anything? Yeah, or Alicia, sorry.
If a crack does start, the material is already under strain, so
Yeah. Yeah, think on a very micro scale, cracks are just atoms splitting and breaking bonds. So you've already preloaded this thing under tension. It's that much easier for it to break right there. So yeah, that's a very good guess, right? Any other thoughts come to mind? What do you care about strain? Chris?
I have a question about it. Does one dislocation cause more weakness than another material?
You mean edge versus screw?
Mm-hmm.
I couldn't say offhand. I'm not, this is outside of my expertise. I couldn't say for sure. So think about this. Let's say you've got a defect, right? The niobium going into the titanium, for example. Niobium's smaller than titanium. Is it? Let's say it's smaller. I don't know if it is. If it's smaller, where's it going to go in the lattice? It's going to go somewhere where it minimizes lattice distortion. If it's smaller, then where's it going to want to sit? If there's a dislocation nearby, it's going to want to sit right here, right? So it becomes really important when you have impurities, because impurities and dislocations have like a symbiotic relationship. They're both causing stress in the lattice, which they don't like. So if you've got an impurity that's causing, it's too small, and you've got a dislocation that has a region where it's too crowded, they go together nicely. If you have something that's too big, let's say you're sticking a big atom inside of there, compared to the host atom, it's going to want to go right here, somewhere where it's already being pulled apart, so just put a big atom there. So dislocations and impurities become really important. It's hard to separate the two because you have to go up in energy in both regards when they separate. It's lower in energy when they come together and they stay put. Yeah?
So would they tend to cause more of an interstitial or a substitutional when they're trying to get in there?
Let's just consider substitution for right now. So this is why sterling silver, even though you started out with pure silver and you replace it with something cheaper like copper, is a better material because it's harder, because you put in a copper which is the wrong size Therefore, I don't know if it's too big or too small. It's probably too small. Therefore, that copper, even though you only add 8 weight%, they sit right here, right? And they don't move around very easily because that's diffusion of atoms, which we'll get to in a few chapters. Dislocations can move much easier than atoms can on their own. We'll talk about how they move later. But if there's a dislocation, there's an impurity here that's not moving, then the dislocation's not moving. If the dislocation's not moving, you made a harder metal, right? All of a sudden, your sterling silver doesn't scratch as easily, right? So we'll come back to that. We'll talk a lot more about that in chapter 8. Okay. So how do they move, actually? We have it right here. Again, we're going to come back to this more in chapter 8, but imagine here's our extra half row of atoms right here at the point called A. If you apply a shear stress to this, so you're pushing right here and you're pushing right here, what can happen is this extra half row of atoms, these things can say, hey, let's just bond right there and break that bond, right? And now you've got this scenario, and it can do it again until it goes all the way over. And now macroscopically, if you get enough of these things happening, you can get some additional deformation, right? But it depends on these dislocations being able to move. And like I said, if you have something that keeps them from moving, you made your material harder and stronger. We'll talk way more about that. Okay, that's one-dimensional defects. I'm not going to say more about that. There are other courses in mechanical engineering as well as material science where you'll learn a lot more about it. All right, two-dimensional defects. A two-dimensional defect is sometimes called an interfacial defect, right? So this is, for example, where you have a boundary separating crystals of either different phase or even different orientation. So right here in this big green weirdo pattern, right, you've got some orientations that are easy to see, right? So you've got like this thing is oriented like that, but this one here is oriented like that. And I think I've been drawing this early in the semester that these things just don't always match up. Like these things don't match up. So you've got like this weird broken region in between of them. That's about an atom or two thick. That's known as a grain boundary. Even though this is all the same phase, because they're in different orientations, when they meet, there's a problem. That's called a grain boundary. It's a problem because on average, everything wants to have 4 nearest neighbors. But here at the grain boundary, some of them have more, some of them don't have enough. So it's either broken bonds or you're trying to stuff atoms in where they don't want to be, right? So that leads to surface energy, which is why since it's an area, it's joules per some area. Joules per meter squared is a common way to report this, right? So to minimize surface area, this is why droplets form. This is why rain droplet forms, right? Instead of just big sheets of rain just floating down to the earth, we have droplets because they're trying to minimize their surface area, right? You have what are called high-angle grain boundaries and low-angle grain boundaries. A high-angle grain boundary versus a low basically just takes into account the degree of difference in rotation, right? So let's show you some examples, right? You can have, so imagine 2 of them that are very close, like these 2 right here, right? This purple line here is very close to that one. They're not off by very much. So that's a low-angle grain boundary, right? Because they're pretty close. It's not bad. And then you can have high ones, right? So somebody clever realized that, okay, if we take this drawing on the left and we draw a schematic of what's kind of going on the right, you could estimate the distance between these grain boundaries from here to here if you know the angle of mismatch, right? So not in the 50s, but later on when they got much better microscopes and they could actually look at atoms, they could measure the angle between this and that, and they say it's 2 degrees or 3 degrees or whatever it is. Once you know that angle, you can use a simple geometric argument to figure out how far apart your extra dislocation must be. So in this case, this is the grain boundary, and the grain boundary is just made up of a series of vertically stacked dislocations, edge dislocations, right? Does that make sense? Everybody see the edge dislocations? Extra half row, extra half row, extra half row, and they're just kind of stacked on top of each other. Why would they stack on top of each other real quick? In terms of strain. Yeah, this is our compression, but underneath each one of them, that's under tension, tension, tension. So the tension and the compression kind of equal out. So again, if you move these, you can, but you have to go up in energy to do so because this is happier in this state, right? So what somebody clever realized is that, okay, this kind of looks just like this. You've got a Burger's vector, you've got a distance between them, and you've got half of the angle, right? That's the angle divided by 2 separating these things. And so the opposite, right? If you guys remember junior high, SOHCAHTOA, right? Sine of the opposite, or sine of the angle equals opposite over hypotenuse, right? So sine of our this is going to equal the opposite, which is our Burger's vector, B, over the hypotenuse, the separation between them, right? H. So using that very simple argument, they can approximate it and say the sine of a small angle is just equal to that small angle. If you guys remember that, sine of 1 degree is just 1 degree basically. And why can we say that again? Why is the sine of a small angle just equal to the angle? Where's that come from? I mean, we all just know it is, but why? Well, if you look at sine, what does it do? Between 0 and 2 pi, sine does this thing, right? But at very low angles, that just looks linear. It just looks linear. And because it's linear, sine of it is just equal to it, right? Over a very small angle. Anyway, so once you have that, you can say that the d, the distance between something, between these vectors there, between the two dislocations, right, is just going to be approximately equal to the Burger's vector divided by the tilt. Okay? That's all. Okay? Okay, so at grain boundaries, there's other problems, right? We know that atoms don't match up just right. So again, if you have a big atom, something that's way too big, it could go in the middle of the lattice. Like, let's say we had like a big person. I could either put them in the middle of this. It's the most un-PC thing I've ever done in class, right? I could either put them in the middle where it's like crowding, or I could put them on the edge row where there's less crowding. Same as like on an airplane. If you got a big person, they don't want to sit in the middle. They'd like to sit on an edge where they can sort of like lean over on the edge a little bit. Atoms are the same way. Atoms are just like people. Okay, another type of two-dimensional defect is what's called a twin boundary, right? A twin boundary. A twin boundary is a special type of grain boundary because it has mirror symmetry, right? So here's one. This you just say like, oh, okay, you got one orientation here, you got a different one there. That's just a grain boundary. But this is a special type because it has vertical mirror symmetry. Do we see it? Right, so here's the twin plane. Again, this is a two-dimensional area it's operating on. And that is a vertical mirror, right? So this atom and that atom match up. This one, that atom. This one and that atom, right? It's got a mirror, right? Now they've put another one, right? So they've drawn another twin. This one has to be the same. That atom, that atom, that atom, that atom. Because there's two planes, we can't keep on going further, right? So that is a twin boundary, okay? So it's not just a grain boundary. It is a grain boundary, but it's a special kind of grain boundary. It's one that has a vertical mirror, right? And these are pretty common in some crystals. Okay. You can also get stacking faults. If you guys remember back 2-3 chapters ago when we talked about crystal structures, we said that the FCC lattice, which is cubic, looks just like the HCP, except we stacked them in different ways. We showed tennis ball pictures and so on, right? We said that there's ABC versus AB. Well, if you take these layers and you mess it up when you're putting it together, you have a stacking fault, right? So let's say that normally it wants to have like an ABC, right? It wants to go A, B, C. And then it wants to start over again. A, but instead of having a blue B layer, it got another C layer, right? So that is a stacking fault. It messed up how it is stacked. So that's a type of defect that can exist, okay? Okay, I'm not similar with that. Next one is a phase boundary. Okay, so we know that there's different phases. We've been calling them alpha and beta. Then a few chapters ago we said, oh, those actually correspond to things like FCC versus BCC. So imagine that you're taking a pure material of just the white atoms and you start adding black atoms. If the black atom is sufficiently different in terms of electronegativity or size or whatever, eventually they won't just be an alloy. An alloy means just random. But they might say, hey, it's better for us to organize, right? So these things come together and they form now a separate phase, right? This is called phase separation. They formed a separate phase within the host phase, right? So the white material with a few black atoms, it reached its solid solubility limit, and now the black atoms phase separated. Now, they don't have to be a pure phase. You could have a mixture, right? This one is like a rock salt, where it does form a second phase, but it's an ordered one of white and black, right? This one was just pure black atoms, right? So you can have different boundaries between these phases, right? So take a look here. The black atoms were more closely bound together, so that led to stretching along the interface, right? So that's a strain because they were smaller. Here, it's a nice coherent interface. Here's an ordered one, right? So basically, that interface could have an energy associated with it because it doesn't match up very well, okay? So that's phase boundaries. And then we also have things called ferromagnetic domains. We're going to come back to this later when we get to chapter 12. For right now, think of it as a region within the crystal that might be a grain boundary, but it could also be smaller than a grain boundary, that has some polarization. That could be a magnetic polarization, so it has magnetization, or it could be like a dielectric polarization, right? So you could have dipoles pointing one way, like all different ways, right? So these could be grains, or this could all be one grain, and there's just sections inside of a grain where this is happening. We'll come back to this later because they become really important for magnets and dielectric materials. And then a three-dimensional bulk. Three-dimensional is a bulk defect, so we've done point defects, line defects, planar defects, finally three-dimensional. These are things like cracks or pores, big second phases that aren't just planar, right? Inclusions. So the question then, in our last 10 minutes of classes, we know these things hypothetically can exist. We've drawn little cartoons that they might be able to exist, right? How do you actually observe them in materials, right? How do we test for them? How do we know if they're there? There's a couple things we can do, right? First off, you could just look at it, right? Sometimes, have you ever seen a street post where it's got like, you can see like the grains kind of splotchy looking? You know what I'm talking about? Anybody seen that before? It's just like they reflect a little bit differently and they're big enough, like almost the size of your pinky. So sometimes these grains, in that case they might not be grains, sometimes they are, they're so big that you can see them with your naked eye and you're like, oh, something's going on there because it's humongous. But our eyes can only go down to not very small. What is it? I've got like 50 microns. Like a hair is 20 microns. So if you have garbage vision like mine, you can't see much smaller than that. And even if you got great vision, you're not going to see below 10 microns very far, right? Atoms we know are way smaller than 10 microns. So how do we see these things? All right, we've got microscopes, right? So one of the very first microscopes they came up with forever ago is optical microscope. And this uses light that our eye can still detect. So our eye is ultimately still the one processing the image, right? Light goes through the lens, hits the sample, comes back out of the lens, goes to our eye, and we do something with it in our brain, right? So we process that image. And it depends on light that we can see. We can only see from, what, like 300 to 700-ish nanometers. That's a tiny range, right? So that limits the wavelengths of light that we can use because our eyes we can't see infrared, we can't see UV. Our eyes doesn't know what to do with it, right? For opaque materials, you can only see the surface. That's not very nice. We'd like to look inside of a material, but our eye can only see what is, if it's an opaque material, what's on the surface. That's not great. We generally do it under reflective mode, and we see a difference in contrast due to the difference in reflectivity, right? So this is your material, right? You got a grain boundary between two different phases. Light's coming in, all like hopefully it's collimated, right? So it's all pointing in the same direction. Hits your sample and it's going to bounce back, but these are going to have different orientations, so they're going to bounce back slightly different. And at grain boundaries, they're really going to not bounce back very well to your eye. They're going to go away. So this will look dark. The grain boundaries going to look like a little black line. And in practice, that's what you see. You look at a microscope, grain boundaries look like little black lines because light's just not bouncing back out as well to your eye, okay? If you've got a textured material with very different grains, then light can bounce in very different directions. So now this thing might be, most of the light's not coming back, so it appears dark. This one, most of the light's coming back, so it would appear light. This one is kind of in between. It could all be the exact same phase, just different orientations. And if you look at under an optical, it might look like a bunch of different phases. It could all be the same thing. It's just that light's bouncing back differently to your eye based off of how it's smacking into atoms and doing something, okay? This is all optical microscopy. You can do things to make it easier to see things like grain boundaries. Like if you etch it, etching it is just putting it in acid, a weak acid, so you don't dissolve the whole thing, but you slowly start to dissolve it. Where's the acid going to attack first? It's going to take away the thing that's already costing the system energy, which is grain boundaries, right? If it's going to if it can get rid of like students on the first row here, or students on like the broken grain boundary between, it's going to take out students in the middle, right? So that's what's happening. So it will grow this area, and that makes it even easier to catch light in there and have it not escape. So it makes it easier to visualize, okay? So you'll do this with steel. I know some of you mechanical engineers will definitely have jobs where you will etch metal, look at it and say, oh, there's our grains. We didn't see them before, but now we do because we etched out the place where they were easiest to get rid of, right? That said, the smallest resolution you're going to get to, I can't believe somebody reported this, 200 nanometers. There's no way you're actually getting down to 200 nanometers with an optical microscope. You have to change you have to start playing, if you remember from physics, you're changing the index of refraction, so you're using oil immersion. You're having the light bounce through, but now it's no longer in air. You're changing it and you're immersing this whole thing in oil. Even then, 2000x is that's not a very believable number. So optical microscope only gets us so far. You're not seeing atoms. Even if you could get to 200 nanometers, you're not seeing atoms yet. So we got to go smaller, right? So cue the electron microscope, right? Electron microscopes are amazing, and the reason that we can see smaller things with them is because they can look using light that our eyes can't process. The electron microscope can go down to, this is what our eye can see, about 400 to 700 nanometers. But electron microscopes can use wavelengths of light that would actually cause us damage, way beyond X-rays. It'd be like zapping yourself, it'd be dangerous, right? They can go as far as 0.003 nanometers, right? Because you can shrink the wavelength of light used. So how do we see it? We don't see it with our eye. We have to bombard the sample with the light. The thing has to bounce off, and we have to have a detector that captures that image, turns it into something that our eyes can look at, which is like a black and white image, right? And with using that, you have scanning electron microscopes, which scan along the surface, right? And in light, since you're using such high energy light, it's actually going to go into your sample a little bit. So you're collecting information not only from the surface, but underneath it, 10, 20, 50 microns, depending on how powerful light you're using. So you're getting information from the surface-ish area. Or if you get your sample really thin, you just get it really, really thin with using some techniques that we won't cover in this class, you can actually pass light through your sample. And then you get all sorts of great information. That's a transmission electron microscope. And these things, you can actually see atoms. This is a picture from a transition electron microscope. This should boggle everyone's brains. We live in the 21st century. We live like Star Trek era. We're looking at atoms here. That's very, very, very cool. This, you can go up to 1 million x magnification. We said optical was maybe 2,000, and I doubt that even. This can go up to 1 million. You can literally see atoms. They can now do videos. They can see atoms move. They can take electron microscopy videos. They can do very, very cool things, which allows us to see, if there's an edge dislocation, you can see it really easy. You'd see that this thing is not a nice, perfect hexagonal grid. It'd be messed up in some way. You can see missing atoms. You can see all sorts of things, right? So scanning electron microscopy is not transmission. Again, you're just looking at the surface. You generally use lower wavelength light, which means it limits your resolution. You can't get to 1 million. You go to 50,000x. You can still look at very cool things. Snowflakes forming. You can see them forming in real time inside of the microscope. Very, very cool things you can see happening. What's great is that you can pair these with other techniques like EDS, which we talked about on day 1 in this class, energydispersive spectroscopy. That happens inside of an electron microscope, where let's say you had a material that broke unexpectedly, and you say, "Oh, what's wrong with this material?" You take that fracture surface, you look at it under the microscope, and the first thing you see is this one here. And there's barely anything to see there. So the next thing you do is you do backscatter mode, which really enhances how the light bounces back. And you say, aha, something's there. And it's a little bit brighter because it bounces back more, therefore this must be a heavier thing. And then if you pair EDS, energy-dispersive spectroscopy, you can actually map in terms of area where are different elements at. You say, oh, this thing is a big glob of sulfur and iron. So you have a bit of pyrite. You had fool's gold grains sticking in your material, which was otherwise, whatever that, boron, magnesium, and manganese, right? So it becomes a very, very powerful tool to figure out what went wrong. You say, all right, where is there pyrite in our processing? Oh, well, we're buying it from this mine, and they've probably got pyrite there, right? It becomes a very powerful tool, and we'll pick up here next time. I think we're at the end. That's the end.